Hello and welcome to PMCD Maths, and we're looking at finding the nth term of the quadratic sequence in this session. And you can see I'm going to use the Rubik's Cube at some point in this to actually link it to something that students are familiar with. As usual, here's the rationale. You can pause this and read this in your own time. I'm not going to pause now. And sequence of teaching. A little bit more different here because I've included this painted cube investigation. Investigations have gone out of favour a little bit, I think, over the last few years. They don't seem to have them so much ingrained in schemes of work, but there's always ways of weaving these, I think, mathematically rich activities in. It's something practical. It's something different. It breaks up the flow of the teaching sort of experience that students have, the learning experience they have, because it's something practical they can work on. You need a range of mathematical skills to be able to access those. And you'll notice I put with those double-ended arrows there because you could do the painted cube investigation and then come on to linear and quadratic sequences, and then later on, explain how to find the nth term of a linear and quadratic sequence, and then refer back to say, look, you've already done this when you've done this investigation. Or probably my preference would be to do the nth term. To do these lessons, how to find the nth term of linear and quadratic before approaching the painted cubes. They've got the tools to actually find those sequences, and obviously the other sequences that you can go on to. And I think I will be doing a Fibonacci sequence video at some point. Okay, so painted cube investigation. If you are brand new to teaching, this is the first time you've come across this, you may have done this at school yourselves. But if you haven't, the essence of it really is you've got a Rubik's Cube, or painted cube as it's called, and you can imagine if you're trying to do this, you're frustrated with it, and you've dropped it on the floor, and it shatters into how many other cubes it makes up this big Rubik's Cube. And you want to put it back together again. How many cubes would you expect to have? Two colors, one color, zero color. And what I mean by that is, so for example, two colors would be this cube here has got two colors. Okay, this cube here has got one color. And you put your own coding. I mean, I've seen people actually put the numbers on there before. This is students, and I've done this as well. So this has got one color, and this one's got two colors. This one's got two colors and two colors if we turn the cube around. So a lot of 3D stuff going on here, and you can get them to draw the cubes with isometric paper. You can start talking about surface areas and volumes, and you've got the language of faces, edges, vertices. There is so much to be gained from this investigation. I really love teaching this one and letting the students discover rather than telling them what's going on here. The sequences you get out here, I mean, I'm not going to spoil this, you can have a go at it yourself, but the sequence you get for how many cubes have two colors is linear, and for one color you get a quadratic sequence, and we're going to come back to that in a little while when we go through this. Again, just a point on this, if you haven't done this and this is the first time you've ever done it, it's a good idea to get them to, when they're explaining how the sequences work, how they work them out. I mean, they can literally count them. How could they actually work them out here? So, for example, the one color in the center here, well, that's on the face, isn't it? And it's on the face of there's one on every face. So that makes, you take one face, we say, well, there's one cube with one color on that face. There are 6 faces. 1 times 6 gives us 6. That one there. Same here. How many on the 4 by 4 by 4 cube? There are 4 cubes of one color on one face. How many faces are there? 6. 6 times 4 gives us 24. Now, this is not something the whole point of investigation is they're trying to discover methods. You're trying to tease that out of the students. If you go in and start telling them how to do this straight away, you're letting their brain become a bit lazy, really. So the idea with these investigations, if you haven't done this before, and I know most of us have done this, but if you haven't done it before, the idea is that you're trying to make them do the work. You know the answers, but you're going to release them only as and when they really, really do get stuck. And then even then through prompts, not through direct, what you do is you count the numbers on one face and times it by the number of faces. I mean, I said that kills their enthusiasm for actually trying to find something, and they just become lazy and look to you for answers all the time. Anyway, that's enough about that investigation. You can probably look online, you'll find examples of different ways people have done that investigation, and maybe I'll do something on investigations at some point, actually, in a bit more detail, because I really do like this one. And there 3 or 4 really excellent investigations you can bring in and link into stuff they've done. They're going to be studying as well. And the great thing about this, I mean, if you can learn yourself how to do the Rubik's Cube, or maybe you can even do the Rubik's Cube. I know I've only just recently learned how this, and this was because I wanted to, just a bit of showmanship in the lesson. It actually, it does wow them when they actually see you've got a mixed up cube, and then suddenly, you do that last turn, and then all the faces appear the way they should do on a Rubik's Cube. I've had students go off and they're inspired, and they go off and learn how to do it. In fact, they get better, way better than I can do it. So it sort of adds to your little reputation as a teacher, actually, who actually looks at fun ways of actually seeing mathematics in the real world and introducing it to them. So, the downside of the quadratic sequence, I mean, you could just teach this, and I've gone to a different sequence here. You could just teach this as a sequence of steps, and they'll get it. It'll be quite dry, By adding these little bits of spice in, like this Rubik's Cube, it just lifts the topic, and they can suddenly start to see, actually, maths is around me in everyday objects. It's not, this teacher is not making it up. You've got to have examples, and you can actually show a physical example in front of them. I've moved on to a different sequence for reasons you'll see in a minute. So I'm going to come back to that quadratic sequence. And by the way, as a spoiler, if you haven't done this, this is quite nice when they come to explain it, this one here. If you look at it, the quadratic sequence comes from the number of cubes with one colour. Look, it's even a square. It fits into the rule perfectly when you come to explain how that sequence occurs. So you get it from there, but you have to tweak this. You have to approach the sequence in a slightly different way. So I wouldn't use this one as your first example. You might do it later on in the lesson once they've mastered it, so they can see, actually, we need to adapt the way we actually approach using this method. So we're still using method of differences here for n squared. And if I remember the first time I taught this, I hadn't actually learned this at school. Hadn't come across it in any way. So it's the first time that I really saw it was in this textbook, and I understood it. I did understand it, but it took me a while to sort of get my head around, why are you doing this? What, in my head, I'm asking why. So the purpose of this is actually to answer some of those questions, why. And as I said in my rationale, if you do too much of that up front, there's too much to remember. The kids will be overloaded, and you're going to have a very difficult lesson. So we don't do the why in this case until after they've mastered it. And sometimes this happens with maths. I think it's just saying, look, accept this for now. I am going to explain it, but accept it. Just go with what I'm saying, and I'll answer that as we come along here. Okay, so as explained here, I always, important thing obviously is to label terms, and we go for methods of differences to start off with. So they as if they're approaching it like they were solving a linear nth term. And we've got 7, what have we got there? 13, 19, and 25. The first difference is all different, so it's not linear. So do we find the difference of the difference? Difference of the difference, and I should put signs on here, actually, because we do have increasing sequences and we have decreasing sequences. So my second difference here, is plus 6. Okay, now we say, because the difference of the difference is plus 6, we know that it's an n squared. And I say, why? And say, well, come back to this. We'll come back to this. And not only that, even more mysteriously, the coefficient of x squared is going to be half of this second difference. That's a bit mind-blowing, isn't it? So what it's saying is it must involve 3n squared. Okay, now, while I'm doing this, what I do normally, another part of the page, is I'll start building up the rules. So say the rule, nth term rule, 3n squared. So I said, we've got that now. We know that that's part of the rule. Okay, and this is where you have to be careful in your wording here. Okay, 3n squared forms part of this sequence. So what I need to do is work out what 3n squared is worth each term in the sequence. So I'm lining up with 1 here, and I'm saying 3 times 1 squared is 3. 3 times 2 squared is 12. 3 times 3 squared, this one here. So I'm looking at n again, and I'm lining it up here so you can see what's going on here. 3 times 3 squared is 3 times 9, which is 27. 3 times 4 squared is 48. 3 times 16 is 48. 3 times 5 squared, 3 times 25 is 75. Okay, now what I'm going to do, I'm just going to do some different colour here. We're saying that this is in that sequence. What I need now to do is take it out of that sequence to see what's left. So we know it forms part of that sequence. What's going to be remaining? What's going to be remaining? So the sequence has got 5. 3n squared gives me 3, the value of 3 from that. So the remaining of that is 2. 3n squared is 12. It gives us 12. So 12 minus 12 is 0. 3n squared gives us 27. That's 25. So how much of that's going to do? 25 minus 27 gives me negative 2. 44 minus 48 gives me negative 4, and 69 minus 75 gives me negative 6. Now, this might seem a bit weird, this bit down here, but what he's saying is essentially that makes up part of that sequence. We need to subtract 3n squared from the sequence to see what's left. We get these negatives here. So, okay, this bit now, we almost don't need this. Okay, we can almost start again. So we put a line through it and say, look, don't get confused by that now. We're starting again now. We've used 3n squared. Now let's label again. And let's find the nth term again. What do? We find the difference. And this time it's negative 2, subtract 2, subtract 2. And they can see, okay, that's not too bad actually, because that's just the, that's going to give me minus 2n. And then I work out what minus 2n is going to give me. So now, all we're doing now, it's important to say is, look, you're doing what you did when you found the linear nth term now. You've done the hard bit, you found the 3n squared, you've taken it away, and now it's just what we did when we did the linear nth term. So minus 2n, again, I'm lining it up in line with what n is. So minus 2, 0, sorry, minus 4, minus 4, minus 6, minus 8, minus 10, or negative 10, 2 subtract negative 2. Well, I mean, you probably don't want to do that actually. What you're going to do is say, oh, it gives me minus 2, I want it to give me 2. What do I have to do? I'm adding 4. Does it work? Add 4 here, add 4 here. So it's plus 4. So my rule is I've got a minus 2n and I've had to add 4. Okay. So what do we do now? Well, we need to check. Let's have a quick check. Okay, I'm going to choose n equals 3. So just choose one that you've got in there. So 3 times 3 squared minus 2 times 3 plus 4. 3 times 3 squared is 3 times 9, that's 27. Minus 6 plus 4, and that gives me 25. And that's what we've got there. So that's how I would teach it. Okay, you may need to go through it a few times. Any questions? Yeah, why is it half? Why is it half? Why is that n squared half? And so, look, we're going to do a few of these. Just take it from me. Just accept it now that it is a half. You know, half of this second difference. And we'll go from there. You know, I'll come and explain that later. They may ask, oh, what happens to the difference of the differences? That gives you a cubed. Well, you can show this in the same approach as we're going to use in a minute as well. Okay, so just a word of warning then, what I do if you do get time, you could go on to looking at the Rubik's Cube one. The only thing to remember with this one is n, this one here, which is 6, isn't it? That's the number of cubes with one colour is 6. That's when n is 3. I'm saying n is the cubes on one side of the cube. So you'd have to put, in this case, you can still do it, 3, 4, 5, 6, 7. So what we're doing is actually adjusting it. We're adjusting how we use the nth term. So that's why I haven't used that as an example straight away. It's something you can throw in maybe as an extension task when they've mastered this. Okay, so why does it work? Why does it work? So you sort of reverse what's going on here. I say, well, look, hold on. Everything we've got here is a quadratic sequence. So what we've got is our quadratic nth term is going to look like n squared plus bn plus c. Okay, so if you look at the one we just had a minute ago, it was, what was it? It was 3n squared minus 2n plus 4, wasn't it? Okay, well, a would be 3, b would be negative 2, and c would be 4. Okay, so just showing what that actually means. Then I'll go through, so okay, let's do it as if it was an squared. Let's use the algebra to show what's going on here. So what would the first term be? Well, n is 1, so we get a times 1 squared plus b times 1 plus c. So we get a plus b plus c. When n is 2, you get 4a plus 2b plus c. When n is 3, you get 9a plus 3b plus c. And when n is 4, you get 16a. And this plus 4b plus c. And this is true, isn't it? This would be algebraically what any term of a quadratic sequence would be. First difference then, what do? We subtract them, don't we? So what do we get? Well, we get 4a minus a is 3a. 3a plus b. 3a plus b. And this one here, we're going to get 5a plus b. The c's will cancel. And 16, that will give us 7a plus b. So you can see that the first differences are all different. The second difference then, 5a minus 5 gives us 2a. But these disappear, 2a. Right, so this is what we had. In our example, we had the second difference was 6. And a is half of that, isn't it? Because 6 is 2a, so a must be half of that. And so you can show this, this is why it works. So, just relax now and understand what's going on there. What would I follow this up with? Well, then I'll also go back and try and find something at GCSE and get a bit more interesting. Some interesting questions like this one here, which requires you to use simultaneous equations to work out what's going on here in the first one. And then you've got a different quadratic sequence below there where you're actually going to do what we've been practicing. Okay, so I hope there's something of interest. Like I said, it's the subtlety and explanation that's really important to make sure that this part goes clearly. If we don't take time over this explanation, you'll have hands up within 2 seconds of you setting the work, and that's always an uncomfortable feeling. So anyway, I hope you found something there that you found interesting and that you can actually use in the future. And thanks for watching, and I will see you next time.